Yeah. So ProSAir. Coming to ProSAir is acronym for propagation of shocks in air. So this is an acronym for ProSAir. So it is a computational fluid dynamics code developed at Cranfield University. So you know that CFD is like similar to your finite element method. It is a finite volume method where computational fluid dynamics, all the fluid dynamic problems are being solved. So this uses your AUSMDV hybrid flux vector or difference splitting method. Basically what this method is, your Navier-Stokes equation is there, right? So that equation is reduced, simplified into the form of your linear algebraic form, so that the algebraic form can be solved using your computer, like your system. So these schemes are being applied to the differential equation. So they use this Hancock MUSCL Hancock time integration scheme to solve the time evolution of the problem. The pressure, velocity, temperature, these all changes with the time. So they use this method to time integration scheme to calculate these parameters. So it uses a spherical and axisymmetric symmetry. It takes the advantage of this spherical symmetry and axisymmetry to calculate to reduce the runtime. Basically in your explosion you have a spherical explosion, so instead of calculating the whole three-dimensional view, it only calculates along the radius, and that radius is being once you calculate along the radius, and that will be remapped into the three dimension. So it uses the advantage of the remapping and algorithm, and so that it will reduce the runtime, and we can obtain your pressure history, velocity, density, temperature at a large number of target locations. Is nothing but your gauge points. So wherever you want to identify the parameters, you have to place your target location, so that you will identify the parameters. So another option is it is a window failure model based on safe and glazing hazard. There is an additional feature for your windows failure when it hits, blast load hits the window. So such additional feature is also there, but we are not going to discuss that in this presentation. So coming to the ProSAir features, the ProSAir features supports like your software is supported by Windows, your typical Windows, irrespective of 32-bit and 64-bit, and it runs your you can solve the problem in multi-core or processor multi-core. So you can use your multiple cores. So your 8-core or 16 cores can be employed to solve the problem, which makes the problem solution faster instead of using only one single core, but it is limited to the licensing of your software. Next, when you are simulating the solution, you can see the graphically it also displays how the problem is being solved during the execution. Also it is visible, and another additional features are that you can give a large number of what will say problem statements as a batch command, so that it will solve the problems continuously without your intervention. The only thing is you have to previously define the inputs and you give as a command, then it will solve that also. That is an additional feature, and you might capture the graphical display solution, and you can use it later on whenever you want to study the blast phenomenon or the propagation. So what are the advantages? It is computationally very fast compared to your now state the software such as LSDyno, Autodyne and all. It will take much lesser time to solve the problem. And another thing is that rapid sweep from one dimensional to three dimensional. So as we have previously discussed, the one dimensional problems, first it solves the problem in one dimensional, then it can remap into two dimensional and three dimensional, but it has its own limitations that we will be discussing later on. And input by means of a simple text space. Either you can use your graphical user interface or the simple text file to give an input to the software. So the basic disadvantages are a constant cell size. So constant cell size is basically your air domain. See, your problem is kept inside a air domain where it is meshed. The mesh. So mesh is discretized. Your domain is discretized, and this we call it as cells. So this we call it as cells, and this is only constant. You cannot have a variable cell size, and the variable cell size has its advantages, which is not available in the constant in the software. Another one is constant specific heat ratio. You know the specific heat ratio, how much it is for an ideal gas? Anyone? Yeah, gamma is equal to 1.4. So when your explosion occurs, when the explosion occurs, near to the explosion, what happens is your gas molecules, they dissociate into ions. When they dissociate into ions, so the gamma specific heat ratio is not 1.4 there, it is less than 1.4. So because of this constant specific heat ratio, so when the explosion, near to the explosion, it tends to predict erroneous values. So only at the large scale distances only you get a better result, not to very near to the explosion. The result won't match to the experimental data. So that is one of the limitation. And another major limitation is your explosive charges are assumed to be ideal. So only ideally spherical. So always the software assumes your explosion as a spherical charge. So this is a limitation. So if we say in case if we have a pipe bomb, so if you have a pipe bomb, then also you have to simulate it as a spherical charge and you have to run the simulation. So that is a major limitation, because the shock propagation is not uniform in pipe bomb. You will have a oval shaped propagation, but we are assuming it as a spherical, so that is a limitation. And another one is afterburning. So anybody has did sir discuss about afterburning effect? Anybody knows? No idea? So I'll tell you. Afterburning is basically, see, when explosion occurs, the initial energy released is due to incomplete combustion. So as the shock wave expands, the additional oxygen is available for complete combustion. So after the initial peak of the shock wave is released, and additionally after some time energy is released. So that effect is called afterburning, and that is not available in this software. Another one is you cannot input geometry from CAD packages. So basically, if you have a complex shape, like you have modeled in SpaceClaim or SolidWorks or anything, you cannot import that into your software. You have to rely on the geometry, limited geometry available, say only cuboid, sphere, cylinder, wedge. These are only available in the software. So you have to rely only on such kind of structure. So your complex structure should be idealized as a cuboid or a cylindrical structure only, and you have to apply the loads. So that is one of the limitation. And flow field itself cannot be post processed. Basically at each instant of time you cannot get the data, only you can get the pressure history. But say after 5 seconds, if I want to get the data, then you have to stop the simulation at 5 seconds and obtain the data. It is like that, but you cannot, after the complete simulation, you cannot get the data at 5 seconds. It's like that. So coming to the basics, detonation. So first we have to know detonation. Anybody has an idea about detonation? Please, you can interact. I think it is a very small. Uh, Sir has explained about detonation. Anyone? Okay. So we will go to much basics of that. Basically, when your explosive material is there, so say one explosive material is there, I will initiate a reaction. Basically, you ignite the charge, ignite the charge or the explosive. So when you ignite the explosive material, so infinitesimally small shock is induced into the explosive material. Okay. So when the infinitesimally small shock is induced, it compresses your explosive, undisturbed explosive material. It compresses the explosive material, and at that compression, if you measure the pressure, that is von Neumann spike. So that pressure is called von Neumann spike, where the initiation of the reaction occurs. So till that time the explosive is unreacted, but as soon as we induce the infinitesimally small shock, then spike is observed, and the von Neumann spike is observed, and the reaction starts. So at the time of reaction you have very high pressure, this one, but when then the combustion reaction takes place, where detonation products are generated, and these detonation products are basically your gaseous products, and these gaseous products velocity keeps on increasing. So the pressure keeps on decreasing and the velocity keeps on increasing. So when the this velocity reaches the sonic velocity. So what is the sonic velocity? It is root over gamma p by rho. So you should observe it is not the sound speed 340 meters per second, that is the ambient condition. So here the speeds will be much higher. Okay, it can be more than the sound speed. So because the pressures are very high, so at this location, when the detonation products reach this velocity, then this state is called Chapman-Jouguet state, and from this point onwards the reaction is completed and the gaseous detonation products, they expand into the ambient atmosphere. So when they expand into the ambient atmosphere, this is called gaseous expansion, and the relation was given by Taylor. So it is also called as Taylor rarefaction wave. Am I clear with this? Yeah, fine. So the next one. So why we have read about detonation is, now the detonation procedure is not considered by the ProSAir. Okay, the ProSAir doesn't consider the detonation process, but what it does is, whatever the energy released from the detonation process, that it is equivalent high pressure is, that is PCJ state. PCJ state is computed, and this is the initial condition to start the simulation. Okay, so whatever the explosive mass you give, that is converted into the equivalent PCJ is computed, and that is the initial condition for your ProSAir. And when you start the ProSAir software or you run the simulation, so it is released into the low pressure region, or here it is the ambient condition. So when it is released into the low pressure or ambient condition, your shock front is generated. Which is moving into the low pressure or the ambient region, and behind the shock front this high pressure is no more a high pressure, it reduces. So this is the Taylor rarefaction wave which is moving into the high pressure region, and behind the shock front you have another pressure region, high pressure region, but it's not the initial high pressure region. So the unknowns here are the conditions behind the shock front, that is, say your shock front is moving into the ambient conditions. These are ambient conditions. Those are the ambient atmospheric pressure, atmospheric temperature, your density 1.225, and velocity. Here if you say ambient conditions, then you can assume it is a zero velocity. So your shock front is moving into the ambient condition. So the conditions behind the shock front are unknown. So basically you have to compute the conditions behind the state of the gas behind the shock front. These are the unknowns you have to compute. So how does the software compute these conditions? So you know the control volume approach you would have read in your BTech second or third year. So using the control volume approach, and you apply the control volume approach and apply the mass conservation, momentum conservation, your energy conservation principles, and again you will be using the gaseous equation of state. Gaseous equation of state is like the relation between PV, that's simple, that PV is equal to nRT, such relations are being used, and using those relations your ProSAir will be computing the unknown parameters. So this is how the ProSAir software computes your unknown parameters. So coming to the blast problem, how do you simulate, how do you apply inputs into the situation? So we consider a situation where a van with an explosive detonates, and the energy released is hit onto the structure. So what is the pressure here? Anybody knows what the pressure comes here on the surface? You have identified? Yeah, so as soon as it when the shock propagates in this direction, so this is the incident pressure, and when it hits the structure, this is the reflected pressure that is being applied onto the structure, and from the sides the shock travels along the sides, and the pressure on these sides will be the drag pressure. So this is a typical problem statement you encounter in general situations or a terrorist attack or something. So in that situation, what are the inputs required? So your inputs required will be the weight of the explosive, type, and shape. In general, specifically you require the shape, but whatever may be the shape, in ProSAir you will be modeling as a spherical charge. So next parameters inputs will be the height and the distance. Height of the explosion, how at what level the explosion occurs from the ground level, and what distance it is from the building. So these two are the another major parameters, and the dimensions of the structure. Obviously you require the dimensions of the structure, and based on this you will decide I want to do a two-dimensional analysis or a three-dimensional analysis. If I have to do the two-dimensional analysis, then I would be planning a cross-sectional shape at the center of the blast and along the length, and this shape, this would be the domain which will be I will be idealizing it. And if I have to model a three-dimensional structure, then it will be a three-dimensional domain I have to model, and three-dimensional model I have to model, and in between, such that your structure and the explosive should be inside the domain. So these are the assumptions you require while simulating a blast problem. So setting up the problem. So in our case, I have taken a 100 kg explosive which is at the 3 meter distance from our structure, and it is 1 meter above the ground. And the dimensions of the structure I have taken 5 meter, 6 meter and 4 meter, 5 meter length. This one is 5 meter length and 6 meter width along the y direction, and Z is 4 meter. So these are the dimensions of the structure, and the domain size I have taken 10 meter by 10 meter by 5 meter. So this is the total domain size, so that the entire structure and your blast charge is inside the domain. I have taken such a way, and the grid size or the cell size I have taken 50 mm in this case. So when you install the ProSAir, first you have to go to the file and new simulation. Always go to the new simulation, unless you want to use your old simulations. Go to the new simulation, and after that option, selecting that option, go to the simulation part, where simulation the options will be open, settings. Unless you use the new simulation or load from the file, your simulation, this won't be available. And after typing this, after selecting the new simulation option, the simulation option opens, where you have to go to the settings file. In settings file, you have 3 options, there are 4 options. Those are the general settings, spherical geometry, cylindrical geometry and 3D geometry. In general settings, this general settings is for all the spherical, cylindrical and 3D geometry, where you have to decide upon the type of analysis you will be doing beforehand. So previously we have assumed that either we will be doing a 2-dimensional or a 3-dimensional analysis. So based on the 2-dimensional or 3-dimensional, you have to select the option. So if I have to do only 2-dimensional analysis, then I will be selecting only the spherical geometry and cylindrical geometry. If I have to do the 3-dimensional analysis, I will be doing spherical, and cylindrical and 3-dimensional geometry, all 3. Or else you can directly skip the cylindrical geometry and directly you can remap the spherical geometry into the 3-dimensional geometry. Whatever may be the case, always you have to choose the spherical geometry first, or else there would be no results. You will not be getting any result, because spherical geometry first calculates the blast parameter, initiates the blast parameters. So now coming to the number of threads or CPU cores, here you have the option to use how many cores based on the cores available in your PC and the limitations of the license. Say this license is only for 4 cores, so maximum I can use your 4 cores to solve the problem. So another option is the switch time. So switch time is basically the problem is solved in first order accuracy, and after some time it switches to the second order accuracy. So if you the switch time is too less, then there would be the simulation might not run if you switch early in the second order accuracy, and if you switch very late, then the results will be little erroneous. So you have to take care of the switch time, and they have given a relationship. The ProSAir recommends a relationship: switch time is equal to 1.2 into 10 power minus 3 and cube root of your equivalent TNT mass. So if you are taking 1000 kgs, then 1.2 into 10 power minus 3 into cube root of 1000. So that would be the switch time you have to input here. So be careful with the mass, and based on that only you would use the switch time. So other conditions, atmospheric conditions, unless you are doing in a high pressure environment, your simulation, you keep these conditions same. You don't have to change these conditions. And intervals is basically if you want to save some states. like I have to simulate after 5 milliseconds, I want the software condition state of the solution, then you use these checkpoints. And coming to the target points, these are very important. The target points are velocity target data. See, if you want the velocity data, then you have to choose this option. If you don't want the velocity data, then ignore this option. And delay target output, this option allows us to like start recording the data. Say when the shock wave reaches the target point only, it will start recording the data. Say after 7 milliseconds your shock wave reaches the target point, then only it will start recording the data. If you don't use the option, then till 7 milliseconds it will be showing blank space, so you will be confused that okay, it has not recorded the data. So there is a scope for getting confused also, but it will record the data that is there. And another one is move target bad points. So when you are choosing a target point, sometimes when what happens is the target point comes inside the domain, like your structure. Inside the structure, see, it is your domain and the target point is inside the structure. So when it is inside the structure, it cannot compute the data inside the structure. So it is a rigid boundary, so it cannot calculate the data. So what it does is, it will shift the target point one cell, only one cell ahead of the from the current position. So this is very useful if you are somewhere you have not calculated properly and the target point is getting inside the structure, then use this option. And split target file is basically say each target point, it will give you a separate file for each target point, or else it will give in groups, a bunch of 1 to 20 target points. It will be giving your data points, the data from the analysis. So these are the general settings. And coming to the spherical setting, spherical geometry. So see, if you want to start the simulations, you will be using the spherical geometry as we have previously discussed. In spherical geometry, you have three options, say plot. In the plot variables, so when you are simulating the starting the simulation, so what variable you want to see in the simulation? So it is overpressure, velocity, density, temperature. Which parameter you want to see the variation? You have to choose the parameter, and at what interval you want to get the graphical user interface to update. It will update at that interval, and you can save the plots also at what interval it gets updated. And show targets is your targets, what you have chosen, it will be visible on the GUI. Now coming to the detonation parameters. So based on the type of explosive, so say you have TNT, there are limited options of that explosive material here. Only 3 or 4 options are there, and other options is there is another option like so basically there is another option like free option like custom explosive, where you can choose the type of the density of the explosive material, heat of the explosive material, and detonation velocity when you choose the custom explosive option. And coming to the problem parameter time, so the problem time, roughly you have to give the problem time. If you choose a very small time, then the simulation might not complete, and large time, then the simulation keeps on running. So I would suggest you can go by the length of the domain by sound velocity. You calculate the length of the domain by sound velocity and roughly try to keep that as a time period, but then also you have to iterate, but this will be a figure roughly which always satisfies the this is the upper bound where you can most of the simulations gets completed by this time. So CFL safety number, CFL safety number is nothing but, see, when you have different cell sizes, so shock wave is propagating at such a certain velocity, and the cell size is limited, say L. So the time period, the time step, at each time step the shock wave is moved into the other cell, and it computes the other parameters. So the shock velocity into time will give you the length, length of the shock propagation. So if this length of the shock propagation is greater than this cell size, what happens? It skips the cell size and it goes to the other. So this leads to an error in the solution. So in order to avoid this, they have set a limitation that is called as CFL safety number, and it is kept 0.5. Now the cell sizes, as we have previously discussed, you have to choose the cell size, and cell size is very important. You have to do a sensitivity study based on the minimum size of the cell. Your peak can vary, your peak pressure computed can vary. So at below the cell size which your peak doesn't vary is your required cell size to compute accurately. So you should be careful with the cell size consideration. And domain size, based on your boundary conditions or based on your problem statement, you will be choosing your domain size. So our problem, what we have chosen is the explosion occurs 1 meter above the ground. So what I do is till 1 meter I'll try to compute radially, then I can remap into the 2-dimensional or 3-dimensional. So for that I have chosen 1 meter here. And the boundary, coming to the boundary condition, there are different boundary conditions available: stop boundary, transmitting boundary, and reflective boundary. So the stop boundary is as soon as your shock reaches the boundary, the simulation stops and remaps into the 2-dimensional or 3-dimensional options. But transmitting boundary, the simulation doesn't stop here, it keeps on going and the pressure is released outside. And so this transmitting boundary condition, you should be careful, and this simulation will stop only based on your problem time. And the reflective boundary is a situation where your shock hits the rigid boundary and reflects back. So these are the 3 boundary conditions. You should be careful while choosing the problem statement. So target points we will discuss in the cylindrical domain. Yeah, please tell me. See, possible, yeah. See, you can keep any domain size, but since as soon as your shock hits the ground, it is no more spherical here, right? So when your shock hits the ground, see, till it hits the ground, it will be spherical itself. But as soon as it hits the ground, what happens is it starts interacting with the ground surface. So here it is not spherical. So I cannot use a 1-dimensional geometry here, right? So it is limited to the boundary. So you can only simulate as long as your spherical shock doesn't hit any boundary. As soon as it hits the boundary, then it's no more a spherical geometry. The spherical symmetry is no longer applicable there. So I will be only limiting my simulation to the boundary itself, as soon the shock reaches the reflective boundary. Am I clear with this? Yeah. So coming to the 2-dimensional geometry. In 2-dimensional geometry, the cylindrical geometry or 2-dimensional geometry option. So similar to your spherical geometry, you have the plot variables and all. You can keep the things same. And planes, here the planes option will be available. The planes option will tell you at what point or what section, cross section plane, you will be observing your data in the graphical user interface. So say if I use 1 meter by 1 meter, so it will be only showing this location. So it will be showing, it won't show these locations, only it will be showing this portion. So you should be careful what you want to see. And another thing is scale factor. Scale factor, see, we have here 100 is there. Say 100 is there. So when you change the scale factor, so it will multiply the scale factor and it will resolve. So higher pressures will be resolved and only higher pressures will be at LO1, and so it is above 1000 will be only been shown here. So if you want to see the graphical user in the resolution of your shock, where high pressures are there, low pressures are there, then you have to play with your scale factors. Now coming to the 2-dimensional problem, here also you have to set up your problem time. So as we have discussed in the spherical geometry, you try to, based on the domain size, you try to use the problem time, you compute the problem time and use it. And cell size also, you should be careful with the cell size. As you are increasing the cell size, your computational time increases. So, and accuracy decreases also. So you should be careful to what cell size and what computational time you are trying to solve the problem. And going for a very small cell size also, it's not advisable, as it will increase the computational time very much higher. So another thing is 3 meter domain size. Now what we have chosen, our previous problem statement was the explosive occurs at 1 meter from the ground and 3 meters from the structure. So 3 meter will be the radial distance, and height I have chosen here 5 meter, but you can go to 4 meter also. So 3 meter by 5 meter is my domain. Why I have chosen only 3 meter is, as soon as my structure like the shock propagation reaches the 3 meter, then now it will start interacting with the our geometry, the three-dimensional geometry. So till it reaches the three-dimensional geometry, I try to solve the problem in two-dimensional so that it will reduce the computational time. This is only to reduce the computational time. Or else you can directly skip from spherical geometry to, you can skip the cylindrical geometry, you can go from spherical geometry to three-dimensional geometry, but it will increase your computational time. So that is the case. And or else if you want to solve the problem only in two-dimensional geometry, you can use this one. You have to change the domain sizes, and you have to introduce your structure inside it, two-dimensional geometrical structure inside this parameters. You have to use the parameters. So height of the blast, here we have kept 1 meter. So since the blast occurs at 1 meter distance, you will be keeping 1 meter here. If it occurs on the ground, you will be keeping 0 meter, and anywhere height, based on the height, you use this height of the blast option. And CFL number also, here you keep 0.5 only, don't change anything unless your solution is not occurring, then you try to tamper with it, but most of the cases 0.5 runs good with all the simulations. And boundary type, so when your shock front reaches the boundary, then it will stop the simulation and it will remap into the three-dimensional geometry. So target points, so target points are basically at what locations I want to get the data input, like shock data from the pressure or the parameters what we require. At what locations, if you want, you choose the options carefully. So 0 to 3, say 0 to 3, so from 0 to 3 radial distance and 6 in range, so you will be having 6 points. So 1, 2, 3, 4, 5, 6, so 6 points are chosen. So based on that, and from 0 to 5 and at 5 in range, so you will be having 5 points. So it will compute the 5 points, evenly distribute the points according to the range selected. So this is the another option, and what it does is, first it will simulate the two-dimensional geometry and it will remap into the three-dimensional problem. So basically it is solving like a cylindrical domain. It will solve in two-dimensional and it will remap into the three-dimensional domain, and a cylinder will be remapped into the three-dimensional domain. So coming to the 3D geometry, so this similar to the two-dimensional geometry, you have the plot settings, and the parameters here would be the maximum problem time. So you should be careful with the problem time here, as we have previously discussed, and CFL number is the same, and cell size also. Now the domain size, now we have to, whatever the domain size we have chosen previously, like the structure should be inside the domain. So those options you have to calculate and keep it. So roughly I am keeping a half meter or a 1 meter offset from the structure. So my structure I have chosen like 5 meter by 6 meter by 4 meter. So I have used some offsets, and that offset is the domain size I am using. So I have chosen the domain x is equal to 0 and 10 meters. So along the length it is 0 and 10, and along the width it is -5 to 5, where 6 meter is the structure, my structure, and it is -5 to 5 along the width, and 0 to 5 meter along the height. So this will be my domain. Domain size will be this 0 to 5 meter. This will be my domain parameter size. And boundaries, at each plane, at the you have to provide the boundary condition. So x minimum, x is equal to 0 is a transmissive boundary. X is equal to 0 plane is a transmissive boundary. X is equal to 0 means YZ plane, and x is equal to 10 is a YZ plane at 10, and that is also transmissive boundary. And similarly Ymin and Ymax, so that is also Ymin and Ymax will be this the other extremes of the sides of the width, that is also transmissive boundary. So I don't want, if you are keeping a reflective boundary, it will be like inside some cube an explosion occurs and you have your structure placed inside a cube where every side, every wall is reflecting. So it will be a scenario where in some structure it is surrounded by the structures, then you will be using that reflective boundary to simulate the condition. And Here it is always reflective because it is a ground. Z mean is the ground. So ground is always reflective, and transmissive to the top of the structure. It is always transmissive. It will transmit unless it is some rigid obstruction is there. So it is transmissive. So origin of remap of the charge. Here you have to again choose the origin of remap. So I have chosen 0 meter, 0 meter and 0 meter. So at the point already you have two-dimensional blast, and this cylinder is remapped into the three-dimensional structure, and the origin will be this origin will the center of this blast, this location will be remapped at the origin. So that you have to be careful where you are remapping the cylinder domain into the three-dimensional domain. Now you have to choose the obstacle. Obstacle is nothing but your structure. Here there are only limited options as we have discussed. It is cuboid, cylinder, sphere and wedge, and since our structure resembles a cuboid, so the dimensions of the structure I have to use, and you have to give the data in xmin and xmax. So xmin is 3 meter, xmax is 8 meter, so the width will be 5 meter, and the length will be 5 meter and the width is 6 meter. So minus 3 to 3 I have given. You can simulate from 0 to 0, other you can use the other option also, but I am comfortable using minus to plus, and 0 to 4 meter is the height. And the material, you will be using solid material. There are only two options, either solid or air. The material of property, it basically doesn't use much material property, so you don't have to worry about it. Most of the structures you keep it solid, and you can run the simulations. And target points, as we have discussed in the two-dimensional or cylindrical geometry, you will be choosing on that. See, we want the target points on the surface of the structure. So we will be choosing accordingly the dimension 2.95 or 3. I've just placed just before the 2.95. I don't want my target point into the structure, so I've just placed before the target structure. It won't make any error in your simulations. The error will be very minor. So 1 second. So when I solve the problem, again I will explain. I think it just started the simulation. You can see from top view how the shock is propagating on the sides and on the front of the structure. And this is the side view, and this is the top view. This is the side view, and this is the top view, and this is the front view of the structure. And since I am observing at 0, 0 plane, so I am observing at this plane. This will be observing at this plane, so I cannot see the structure. So now what happens is the two-dimensional shock propagates. It's interacting with the ground, and as soon as it reaches, it remaps into the three-dimensional structure and three-dimensional geometry, and it propagates. Since it is top view, you cannot see that after some time only the top shock reaches the structure. So that's why you are not seeing the shock reaching the structure, but shock has already reached the structure beforehand itself, since we have remapped the shock into the three-dimensional domain. Fine. So this will be how the simulation will be shown after, if it is running perfectly, all the parameters you have given perfectly, then this will be how the simulation occurs. And these are your target points where you can observe the data, you can get the data points from the simulation. So coming to the result file. So your result file, when you run the simulation, everything completes, then these are the saved states of the files. So target summary spherical. So first the one-dimensional geometry summary will be provided, then the cylindrical geometry summary will be provided, and then you will get the three-dimensional geometry summary. And other than that, you will get each point data. So each target point data will be also there. So for three-dimensional target point, you will get the target point data separately. So from this you can extract your incident, reflected pressure, all the data can be extracted. So this is a typical result file. You will be seeing a typical result file like this in Excel. When you open it, the CSV format you can open in Excel, and you will be seeing this. This is the summary file where it will show the status OK. If it is showing the status OK only, the data is captured. or else the data is not captured. So you should be careful with that. And at each point, say the target point 1, the location is 2.9 meter minus 3 meter, and z is at the ground level. So you can only identify your target points based on your xyz location. So you should be careful with your xyz locations, and it will give a summary what is the maximum pressure obtained, and at what is the time duration, minimum pressure, and minimum time at what instance of time it occurs, the total impulse. Maximum impulse would be the time history, the integration of your pressure history, that would be the maximum impulse. Maximum impulse, here it is a positive impulse, and total impulse will be the combination of positive impulse and the negative impulse. So these are the things you should be careful while extracting your data. And other thing is your point data. So I have considered the target 78 data. In target 78, the position will be 2.95 meter, and 0.025 is roughly at the center, 0 with center of the structure, and 2 meter height from the structure. So we will be getting the total distance. It computes the total distance, like cube root of this, all these parameter will give you the distance. This you can use to compute the scale distance also, and you will be getting time, the time variation at 7.21 millisecond, my density, my energy, the overpressure temperature. Since we have not chosen the velocity option, the velocity data is not given. If you choose the velocity option, you will be getting Vx, Vy and Vz, that those data also will be available. So coming to the free air burst scenario, different blast scenarios. So free air burst, hemispherical burst. Anybody knows the difference between these three types of explosions? You can tell me. So basically your free air burst scenario is your shock wave directly hits the target, and there is no obstruction for the shock front. But in air burst, it will reach the target, it will reach some boundary before hitting the target. And hemispherical burst, when your explosion occurs on the ground, so you will be choosing the hemispherical burst kind of a detonation. So for all these types of burst, your spherical settings, I'm considering for our case it is 1000 kgs. So I want to show what will be the difference in these three kind of conditions. So 1000 kgs is the initial condition I have assumed, and TNT is the explosive material I have chosen, and here the problem time I have taken 1 second, and all these are parameters you can see later also. So now if I have to use hemispherical burst, then I have to multiply it by factor 1.8. So why 1.8? You know, any idea? Did sir discuss about the factor 1.8 in hemispherical burst? Okay, I'll tell you why 1.8 is. Since when the explosion occurs on the ground, you cannot simulate the crater formation, and some amount of energy is lost due to the formation of a crater. So roughly they reduce it by a factor of they reduce the factor 0.2. So 1.8 is used, or else if you are perfectly rigid on the ground, then the energy is total energy is reflected back, and that the charge mass size should be twice the initial charge. So basically to account for the effect of crater formation, you will be using 1.8 factor. So if you are doing a hemispherical burst, just use 1.8 times your charge mass, that is 1000 kgs here. So 1800 kgs you have to use to create a hemispherical burst scenario. So difference between free air burst and air burst. So when I am using a free air burst, I will be using the height of the blast as 0. So at the ground level only my blast occurs, so not ground level, so it is not reflecting, and it directly is propagating into the free space. So I will be using height of the blast 0. But if I want some interaction with the ground, or it is in interaction with some obstruction, then I will be using height of the blast to simulate air burst scenario. So free air burst scenario, I think it has been discussed in the class, but again, yeah, please. Okay, height of the blast. Okay, that will be clear when we discuss the free air burst and air burst scenarios. I'll be explaining separately. So free air burst is basically the typical example would be, say a projectile explodes or a bomb explodes right above the structure, and the shock wave directly propagates and hits the structure. So that such kind of case is free air burst scenario. In free air burst scenario, the shock is not, since the shock is not obstructed, what I do is, if I have to simulate in two dimensional, I'll consider this case. I'll consider this domain two dimension, and I'll say that my charge is detonated at this point. Okay, understand? My charge is detonated at 0, 0. So charge is detonated and it expands into this region. And here I'll say my structure is available and it hits the structure. So if you see the simulation, you will see in few seconds it is running. So yeah, my charge is at 0, 0. The shock wave propagates, and as soon and it hits the structure directly. So there is no obstruction for my shock wave. So when the shock wave hits the structure, so you can see the reflected pressure being generated. So it is higher than the pressure of the incident pressure. So this is the reflected pressure generated and it moves forward. So this is a free air burst scenario. So there is no obstruction. You just, your shock front has to reach the structure. You will simulate using you will simulate the scenario using the free air burst scenario. So while coming to the air burst, so your shock, either it is some building is there or it is on the ground. So just the explosion occurs some height above the ground. So this is the case where my explosion occurs. Then I want to simulate the air burst scenario. I will be considering in two-dimensional scenario. I will be considering a two-dimensional grid like this, and my structure, I will place my structure here, and the explosion will occur at certain height from the ground. And if you want to see some obstruction, then you can keep some obstruction. Based on that, you imagine where the obstruction should be there, and based on that you put your charge just above the near to the obstruction. So if you see the simulation, so the simulation, it is propagating from 1.5 meter height, and as soon as it reaches the ground, it will start interacting with the ground. So this is how, if I change here my scale factor, that's why you are able to see the resolved pressures. And here you can see the reflected pressure. It is in between these two states, and the max temp formation is very small here. It will take some time to simulate the max temp. You can try to play with the charge mass and distances to generate the max temp, visible max temp here, and it reaches your structure. So this is how you simulate a air burst scenario. And coming to the hemispherical burst, since the charge is 1.8 times my free air burst charge. So 1000, say your explosion occurs with 1000 kg, then I will be using a factor of 1.8 to simulate the hemispherical wave, and here I can get the perfectly hemispherical wavefronts. So this is how you will get the hemispherical wavefronts. So this is the if you see, this will be the side view. Here you can, it is visible, and this is the front view. If you see from here, then this will be the front view, and this is the top view. The top, how the shock wave is, here it is spherical, it will be the shock front propagating into the domain. So this is how these three scenarios you can simulate, and based on these conditions, if you want to keep your structure obstruction somewhere, you can keep your you can model your structure. One can model the structure and in the path of the shock front, and you can get the data, whatever the data required, as we have discussed in the previous examples. So these are the things while simulating the different scenarios. And when you extract the data, say some point reflected data, if I want to extract the data, so the incident pressure I can extract, so there is no obstruction. And if you want to generate the reflected pressure, either on the boundary you will be getting the data, you will be obtaining the data, or you give a reflected boundary on the in the domain, and at the reflected boundary you keep your target point and get the data. So if you want to get the reflected pressure, either you simulate a reflective boundary, and on the reflective boundary, you capture the data, or your object, or that your whatever the building is there, you have modeled, and on the building, whatever the point and and make sure that it is on the surface, on the normal to the blast propagation. If it is not normal to the blast propagation, then you will get the side on pressure, not the reflected pressure. So when I compute the incident and reflected pressure, you can see the incident pressure and the reflected pressure. So you know the factor by how much the incident pressure varies with the reflected pressure, the ratio of reflected pressure to the incident pressure. You know the range? Anybody can tell the range? Reflected pressure to the incident pressure. That is CR factor. CR factor. CR. It is called CR factor. PR reflected by PR incident. Peak. It is yeah, it starts from 2 to 23 or 13. Okay, fine. I don't remember, but it starts with 2 and it ranges to 23. Say. So this is the pressure history. At each point you have to obtain, and which will be which load you will be using, either incident or the reflected you will be using to compute the load. Can anybody tell which pressure you will be using to compute the loads? Not always. You can use the incident pressure also. I'll tell you where you have to use the incident pressure. Where you can you guess? Okay, we will be seeing that later on. I will be explaining in the next slide. So the pressure versus displacement. So here basically you cannot get the pressure and displacement, but you can see the pressure versus displacement in the graphical user interface. How your shock wave propagates and at what distance. See, this is the initial state, and the pressure PCJ is decreasing and it is and the shock front is moving forward, and based on the distance from the shock front, say 0.5 meter, how the pressure is varying according to the distance, that is being shown here. And if you have to compute pressure versus displacement, then at each point, target point, you have to choose at each distance target point, and the time instances you have to compute it. It's very cumbersome. And basically you don't require pressure versus displacement usually in our calculation of blast loads. So you can ignore, but you have to know how the pressure is varying with the distance. This will give you an idea how the pressure is varying with the distance, and at what distance you have to keep your structure to know the maximum pressure is obtained and all. You can get a brief idea about that. So coming to the shock propagation, I think sir has discussed this shock propagation in side view. Did sir discuss? Okay, let me discuss. So say your shock front is applied. See, in our previous case we have considered our three-dimensional structure, and the three-dimensional structure is there. At the cross-sectional level, the shock front is hitting. At the cross-sectional level, I'm trying to see what happens when the shock front hits the structure. So initially the shock front is just before the structure, that we have simulated it. You can simulate this one, and as soon as it hits the structure, then you have a reflected pressure. You have a reflected shock front pressure is being applied onto the structure. The shock front gets reflected, and a portion of your incident shock propagates forward. So this is a portion of your shock front, it's propagating forward, and this portion of the shock front is getting reflected. So, and because there is a difference in the pressure behind this, you have a vortex region or a rarefaction wave is generated. So if you want to see this rarefaction wave, you can resolve the scale factor. You can increase the scale factor to see the rarefaction wave, and this rarefaction wave moves downwards, and this rarefaction wave, what it does is it decreases the incident pressure, reflected pressure on the surface. This is called as the clearing effect. This reduces the pressure that is applied onto the structure. So the reflected pressure is being reduced by this clearing wave, and the shock front moves ahead. So as the shock front moves ahead and reaches the other end of the structure, again you have a diffraction. So whenever you have an edge, the wave front hits the edge, you will have a diffracted wave, and the diffracted wave, the energy is decreasing, and the vortex region is formed, and always the energy is decreases. So the pressures always tend to decrease faster in these regions. So you should be careful while measuring the pressure histories here. So previously we have discussed that the reflected pressure is used to compute the loads, but that is only on the front face of the structure. So here we have a incident pressure traveling forward. So what you will be using here, which pressure history you will be using here? You will be using incident pressure history into drag CD into Q. Sorry, you will be using CD into Q, that is the drag pressure onto the surface. Getting? So that will be the pressure history you will be using on the sides of the surface. So that pressure you will be using to compute the pressure, or you can obtain it from the simulation. So if you have velocity term, then you calculate the drag pressure as dynamic pressure, and drag times the dynamic pressure, you will be calculating the pressure on the surface. Or you can get this pressure history. It's not always the reflected pressure. Here you are having a drag pressure that is being on the rooftop and sides also. You will be having the drag pressure on the sides of the structure also, and that pressure you have to use to compute the loads on the sides and the top of the structure. And as you can see, the shock wave moves forward and the pressure decreases. So again the vortex region is formed here. So this is how you simulate your cases, your shock propagation. You should be careful while simulating the data. So this software is capable of like generating the typical shock scenarios, explosive scenarios, with the limitation of a complex structure. You cannot simulate a complex shape of the structure or the complex shape of the charge. For simple shapes of structures and charges, you can simulate the explosions. So this is end of the presentation. Anything if you want to know, discuss, you can ask questions. So we have another half an hour to discuss, so please. Are you clear? Any doubts or any slide you are not clear with this, you want explanation, please ask the questions. Okay, the moving blast, right? Moving blast, I'm not sure you can use this software to simulate moving blast, but you can use LS-DYNA to simulate such kind of a scenario. There is an option in LS-DYNA where you can generate a moving blast scenario, but in this I'm not sure that you can simulate the moving blast scenario. But yeah, you cannot simulate the moving blast scenario in this case, but you can simulate that in using LS-DYNA. What changes, if you want to see that, if you are considering a moving blast scenario, what happens is different effects is actually shock bulks up. Shock bulking is basically what happens is in first you at one instant your shock wave is generated, and the shock wave keeps on, and at another instant another shock wave is generated. So these two shocks tend to merge with each other, so the strength of the shock increases. So as long as the, say, pipe bomb, so it is linearly, if you are linearly exploding a pipe bomb, what happens is initially the explosive is because of the detonation, a shock wave is generated, and the shock wave further initiates the explosive. So these two shocks merge together and form. So a series of shocks are generated, and all the shocks combined together form a stronger shock. So this will I think this kind of a method is used in your excavation, your coal mining industries and all. They use such as a linear blast to generate a bulking of shock and increase the shock strength to get a more damage out of a smaller charge or smaller explosives. Am I clear with this? See that based on the interval only you will get the maximum output, so that they do the trial and error on the simulations to calculate the interval of the detonation to increase the strength of the shock. Mostly as soon as the shock reaches the other explosive, they tend to ignite the other explosive, so that it keeps on a train of shocks are keep on generated, and the shocks bulks up. So these might be the yeah, tell me. Okay, that okay, I thought you were asking about this one. So this one, able to see the screen? Okay, this one this interval option, right? This is basically at each times units are not there, but it time steps. So the simulation calculates by time steps. Okay, these steps, time step. You can see in here on in this figure, time step. Is it visible? So this time step this is the factor here. At every time step, like 100 time steps, it will save the data. So these plots are saved at every time step. So that is what this interval uses. And you have to choose the option save plots to get the data. And at every interval only, it will update your graphical user interface. It will not show at every single time step. At every 100 time steps, it will update your graphical data. So that is what this option for. Anything else you want to know? No, no, no. The time step is computed based on the cell size. And the cell size, based on the cell size, the time step is computed, and more on that time step, you are applying a CFL safety factor to avoid errors in the simulation. No, no, no. See, your spherical and cylindrical, you try to keep lower cell sizes so that your blast wave is resolved properly. And if as you go for farther distances, you can keep a higher cell sizes also. But it is mesh sensitive. What I want to say is it is cell size sensitive. So if you are keeping very large cell size, then what happens is your peak, as we have discussed, the peak pressure. What happens with the peak pressure is it doesn't get resolved properly. It will show a lower value than the actual value. So it tends to happen that there will be error in the peak pressure. So you have to be careful what cell size you are using it. So that comes with experience, but you can do trial and error and find out the pressure. The peak is not varying, then you can say that I'll keep the cell size to run the further simulations. So mostly these simulations are iterative, so you have to play with the cell size and time steps to come for like to get the proper values to do further simulations or further problem statements. Oh, that one, see, you can see when here, I think, not here. Okay. Okay, here only. So basically, what I meant to say is the scale factor when you change. So the pressure is resolved. See, this is showing your pressure history. Here the option is for over pressure history. So pressures above certain value will be shown yellow, and certain value it will be shown orange. So this one, if I try to apply scale factor, then say your pressure is 1000. Say here the value is 1000. So above 1000 kilopascals, it will be showing yellow. So if I use a scale factor, then it will say scale factor of 10. So only pressures about 10,000 will be shown yellow. So it will try to show the different pressure zones. The pressure variations contours will be properly resolved in your graphical simulations. If you keep a scale factor 1, then you will almost see yellow shape only. So you won't see other subsequent pressure variations. So that is the option you can use. So that the option is here. Here the scale factor. This option, if I change by factor of 10, then this value is multiplied by the factor and you get a better result contour. But there is a side effect also. As the shock wave expands, then it will change automatically change the pressure. The ranges also decreases. Then you have to again reduce your scale factors to see properly see the range, or else it will be only showing the gray scale. It won't be showing other pressure histories. So you should be careful. You can anytime in between the simulation also you can use the settings, and then you can change the scale factor. And another important point is, unless you are changing the star, whatever the marked in star, then you have to restart the simulations, and other things you can change in between the simulations also. So if your simulation is running, if you type the settings option, it will pause the simulation, and you can change the scale factor, at what plane you want to see the pressures, everything you can change except the points marked with the asterisk sign or the star sign. If you are changing this, then you have to, the problem will restart. So that is the additional point I want to tell you. So anything else? So any more doubts you have?